Alright, welcome back to this new video. In this video we will be discussing a forbidden physics shortcut, which, interestingly enough, will derive for us the classical kinetic energy formula without using the WKE theorem, or aka the work kinetic energy theorem. Well, let us start. The first thing I want to talk about is that there's a key term which is called as momentum integral. What I mean by this is that instead of starting with work, we know that work is just an energy transfer to an object or a particle when there's a force acting on it and giving it a distance. We try another method instead of that. We try to integrate the momentum equation, the linear classical momentum equation, with respect to velocity. Okay? So what I mean by this is just let us compute the integral of p dv. Okay? See what that happens. Now, if we substitute the classical momentum p is equal to mv and integrate it into that equation, which I have just showed you, we see that integral p dv is equal to mv dv. We have just substituted the p is equal to mv into here, and we got integral of mv dv. Now we know that mass is just a constant, so we can pull it out of the integral and then easily take the integration. We get 1 over 2 mv squared plus c, and this c, we know that is just a constant of integration, which must be evaluated eventually. Okay? Now, let us talk about this result. Of course, after imposing the initial conditions, say at velocity is equal to 0, that means the object has no speed yet. Of course, the energy is also 0, so c calculates to be 0. Now, we arrive at this result. Kinetic energy is equal to 1 over 2 mv squared. So this is just like what you get for the formal definition of work kinetic energy theorem. So what is the difference? Actually, in numerically, there is no difference. Okay? Because what we have just derived is called kinetic co-energy. Now there's a note to you, students, is that physically this calculates what? Kinetic co-energy, okay, which is the mirror of the actual kinetic energy, which is derived by work kinetic energy theorem. This is the mirror of it. Okay, but in our everyday world, let's say Newtonian physics, co-energy happens to equal kinetic energy. So basically, what I would try to emphasize is that the method, the shortcut that basically gives you the kinetic energy, the derivation, okay? And that's the importance of this shortcut, which basically saves you a lot of time instead of using the work kinetic energy theorem. And I advise you not to use this method on relativity or relativistic momentum, because it will not work. I guarantee you it will not work. So please do not use that on that. This is just a mathematical trick, or basically a happy coincidence. That's just a mathematical happy coincidence that makes it so in classical physics or classical mechanics that the kinetic co-energy numerically is actually equal to the actual kinetic energy. All right? And that's it for this short lecture. Thanks for watching.